Hey everyone, I wanted to give an alternate way of going through this problem. We've been so equation heavy, I miss my graphs. So I'm going to go ahead, I'm just going to solve the same problem. If you like the algebra, if you like the equations, feel free to keep using those. But I want to show you how you would go about thinking about this problem using a graph. So here's what we're going to do. Let's start by remembering what the problem is. Kicker sends a football with initial velocity of 25 meters per second, an angle of 60 degrees above the horizontal. Of course, I already erased all of my, do I have it still in my calculator? Nope. I erased all of my work, so I got to recalculate the components. So the first thing we do have to do is we still have to calculate the components. That does not look like a 60-degree angle. We do know that this is 25 meters per second at a 60-degree angle, and we know that that'll have two components. The horizontal component will be 25 times the cosine of 60, which we know turns out to be 12.5 meters per second. We know that the vertical portion, it will be 25 times the sine of 60, which I'll run through on my calculator. 21.6. Oh, look, it's right there on my calculator. I'm not even paying attention. So 21.7 is what I'll round it to. So that's no different. All right, we can't really skirt around that. Not that I know of. I'm sure someone smart and has a way to get around that. I don't. All right, but let's go ahead and graph things. So what we're really concerned about is, as always, the velocity versus time graphs I find to be the most useful. So I'm going to go ahead and make velocity versus time graphs, but we can't make one velocity versus time graph. We have to make two. So I'm going to go ahead and stack up two different velocity versus time graphs. And when I mean stack up, I mean, let's see if I can draw a straight line. Here, oh, look at this, advanced. Ooh, no, I can't even do it right. So look, I get to make graphs like this. So I'm actually going to stack up two graphs. So so these are both velocity versus time graphs, and I'll even erase. Can I erase this little section here? No, will let me do that. Oh, come on. So I'm going to just go do. Yeah, separate and sweet. Oh, that's going to really annoy Zimmerline. Sorry about that, Zimmerline. So we have our two little velocity versus time plots in here, but this will be velocity versus time in the x, and this will be velocity versus time in the y. Y. So let's think about what these graphs look like. So the velocity versus time in the x, we have the punter, and the punter kicks the ball, and the ball goes up and over. And we know that in the y, the velocity is changing, but in the x, there's no reason for it to accelerate, right? If we were to draw the free body diagram for the ball, there's just the force of gravity downwards. It's the only acceleration we have will be due to gravity. So therefore, this graph is going to be nice and boring. So I'm going to use my straight line tool. Oh my gosh, it's like opening up a whole new world. So this graph will be nice and boring. And as a reminder, the area here, oh, can I even use a rectangle tool? Oh my goodness, I feel so, oh no, I want to fill it in though. How do I fill it in? Oh, like this? No. Oh, forget it. We'll just go ahead and do it the old-fashioned way. So we know that this area here will tell me how far I've traveled, which is ultimately the answer we want, right? We want to know how far it's moved horizontally. Vertically, though, we know that it starts off with a velocity of 21.7. Oh, sorry, we know this one's 12.5 as well. We know that it starts off with a velocity of 21.7. And we know that that velocity is going to be changing, and it's going to be changing because of gravity. So that means the velocity is going to be becoming more and more negative. So I'm going to go ahead and draw this as a negative line right here. And we know that the slope of this line will be -10. So And then finally, I'm going to go ahead and do this in another color, really nice and thin. Can I change how the size of it is? Wherever this thing hits the ground, those two need to match up. All right, so we know that whenever this hits the ground, that's when this stops. So these two lines, that's why I stacked them on top of each other, so we can see how the two are related. And so our goal is going to be figure out when this lands, where is this line that I just drew? And then if this is the line that I just drew, how wide is this? What's the area here? So notice it's actually the same exact structure as when we did it with algebra. But when we think about it with algebra, we just have a list of numbers. I don't know, I just think the graphs are pretty. All right, so let's go ahead and start. Let's get rid of this so I can start thinking about this. All right. What am I doing? There we go. So let's zoom in a little bit. And let's start thinking about what's going on here. We know that the shape of this position versus time graph is a parabola, right? And parabolas are symmetric, or at least this one should be. I mean, it's just the guy's kicking it, it goes up in the air and then comes down. So this is symmetric, which tells us that our velocity versus time plot should be symmetric. So whatever area this is, it matches the area of this. And that makes sense, because this area is the ball going up, and this area is the ball going down. And I think the ball's going to go just as far up as it goes down, right? Also, we know that the slope of this line is -10. Which means that however tall this is, it's 10 times taller than it is wide. So this 21.7 is 10 times bigger than this is wide. So if it's 21.7 tall, then it has to be 2.17 wide. And remember, we said this is symmetrical, so if this is 2.17 wide, this must also be 2.17 wide. So altogether, that's 4.3. Oh my goodness, can I do my math? Can I do my math? Do I really need to pull? I'm sorry, guys, it's been a long few days. So 4.34. That doesn't quite. Does that match what I got last time? I don't remember. We're running with it. Maybe I made an error somewhere. If I did, sorry about that. Yeah, maybe I grounded it differently last time. But I ended up getting 4.34 seconds. And what's fun is I didn't use any equations. I just used basic geometry. Although all that basic geometry I just did is actually the same exact algebra that you did in the previous version. That's something that I don't think is explained to students quite enough. Any single thing that we do in geometry can actually be expressed as algebra, and it actually goes both directions. Now, you have a little bit more freedom in algebra just because it's so abstract, but just so you know, like, so many things that are in algebra can be expressed geometrically. All right, moving on. So we know that this must be 4.34 seconds wide. And it's 4.34 seconds wide and 12.5 seconds tall. Oh, I could run through that on my calculator. Let me pull my calculator over so you can see it again. 4.34. And then 12.5, I get 54.3. So the area to this must be, that's too big, 54.3 meters. So I think that's about what we got last time, isn't it? I am wondering if I have a little rounding error or something in either this version or last version, because I'm not remember that being the exact same. But that said, I think it's pretty close. Watch, they're probably going to be the exact same, and I'm just have a bad memory. So I don't know. I like this sort of solution to the problem. I think it's aesthetically pleasing. But that said, it is literally the exact same thing as the algebra. If you even go back and look at my math and my calculator, I put all the same steps. It's just a different way for you to think about it. And I think it's pretty, and it helps that I can do it in this fun little color scheme as well. All right, everyone, or Zimmerline for being the one person who wants to watch this video. Thanks for watching. I'll talk to you later. Have a nice day, guys.